Hi everyone. Today I will introduce you to Docker, a very popular technology nowadays. My main goal is to focus on the basics of Docker so that by the end of this presentation you will know what Docker is, what Docker can do, and how to work with Docker. Now let's start with a brief view of Docker. As you can see, it has a big community, a lot of downloads. Its users and partners include all famous big names in the world. Its content includes the most popular frameworks and applications. And that was in 2017. Yes, I created this slide in 2017 to introduce Docker to my colleagues. And at that time, Docker is already popular. According to Docker statistic in 2016, Docker has been useful in many aspects. For example, 45% of Docker users have been able to increase the frequency of software releases, 93% seeing some dev benefit, 57% Docker users have seen improvements in operational environment management, 85% seeing some ops benefit, 70% of Docker users say Docker has dramatically transformed blah blah blah. 62% have seen improved MTTR on software issues. Docker is widely used now. In March 2021, it already had more than 11 million developers, 7 million applications, and 13 billion monthly image downloads. That is amazing. So, what is Docker? If you have visited this link in 2017, you would have seen this definition. Docker is the world's leading software container platform. The link is gone now, but I still keep the definition as I totally agree with that. Docker is really the best in the area of software container platform. Docker is a platform for developers and system administrators to develop, ship, and run applications. It has rapidly gained popularity as one of the best tools to build, ship, and run software. You will agree with me more on that when you start using it. Now you have known what Docker is. The next question is, what can Docker do? Basically, Docker can do two things. First, it can replicate the exact environment of the build to any machine. And second, it can run deployments against different environments, for example QA or production, consistently. Typically, an application will go through a few phases and environments from development to deployment. For example, in phase 1, some developers develop the application in the local machine. That is the dev environment. In phase 2, the application will be built and deployed to another machine for testers to perform the testing. That is the QA development environment. In phase 3, the application will be built and deployed to another machine for end users to use it. That is the production environment. Traditionally, the hardware and software configuration of the dev machine, QA machine, and production machine are not the same. For example, the dev machine may use Windows operating system, while QA and production machines may use Ubuntu. Such environment differences can be the root cause of many issues that cost a lot of time to debug. Docker helps to avoid that by providing a consistent container environment. The container environment used in the dev environment will be exactly the same as that in the QA and production environment. As a result, if your app works in dev, then it will definitely work the same in QA and production. In the illustration, an application can be packaged in a Windows server or a Linux container, depending on your company's preference. Then it can be deployed to anywhere from a private data center to a traditional service provider to a modern cloud like Microsoft Azure. One thing to note here is the term container. In transportation, containers are standardized boxes invented to make it easier and safer to package goods for transport. Here, Containers are standardized units that are used to package applications for delivery and deployment. Just as there are different types of transport containers optimized for different transport purposes, there are different types of Docker containers optimized for different application usages. For example, we have containers optimized for development, we have containers optimized for deployment, etc. The next question is who and what can Docker help? Basically, there are three groups of entities that will benefit from using Docker, namely developers, operators, and enterprises or companies. First, for developers, Docker helps to eliminate the works on my machine problems. When a piece of code runs as expected in one developer's machine but fails to run in the same in another developer's machine. That may sound funny, but that has been a popular reality in so many teams. Although working on the same project, different team members often have different development environments set up. For example, some prefer Windows, some prefer Linux, and the rest prefer Mac OS. Even when they're using the same operating systems, they still can use different versions. Windows 7, Windows 8, Windows 10, Ubuntu 16, Ubuntu 18, etc. Thanks to Docker, consistent development environment can be easily set up, as simple as this. If all members specify the same version of the Docker image to use, then the same piece of code will run the same in all members' machines. So simple, right? The next group that benefits from Docker is operators. In a company, operators are responsible for ensuring that all IT services and infrastructure meet operational targets. Their roles include running, monitoring, and tuning systems. Without Docker, they need to rely on virtual machines, which are huge in size, slow in operation, extensive in resource consumption. With Docker, life becomes more productive, as Docker are much smaller in size, much faster in operation, and much more efficient in resource consumption. You will understand this better soon, but for now, what Docker means to operators includes lower cost and higher compute density. Finally, Docker benefits enterprises or companies, and it makes it easier and more feasible to build agile software delivery pipelines. Before Docker, it was possible too, but the process was much harder, more costly, and more error-prone. With Docker, even a small company can build one such pipeline so that it can ship new features faster, more securely, and with more confidence. So, what do you think? Perhaps you have some doubt now. How can Docker do that? If you used to work with virtual machines, you may also wonder, virtual machines can do the same. Then how come Docker is way better? Yes, you are right when you recognize the similarities between Docker and virtual machines. Docker is a great three-factor version of virtual machines in terms of architecture. Docker simply strips out the most ineffective part from virtual machines. Let's look at the upper diagram. As you can see from bottom up, we have a physical server machine. In that machine, we install a host operating system with a hypervisor. The hypervisor is the application that makes it possible for us to install many virtual machines inside our host or OS. For each virtual machine, there are basically three layers of applications: guest OS, bins, lib, and app. If our physical machine needs a host OS, then our VM needs a guest OS. Simple analogy. App is the applications that we want to deploy and run, and bins libs are the dependencies that our app needs. Now let's look at the lower diagram. From bottom up again, We have a physical server machine with a host OS. Here's the big difference. Instead of the hypervisor and guest OS, there is only Docker engine. Wait, a Docker container is equivalent to a VM, but a Docker container does not need a guest OS? Really? Yes, that is real. If you compare the diagrams again, you will see that the removal of guest OS is truly great, and it makes Docker containers super lightweight compared to a VM. For example, if we create a Windows-based VM, the guest OS itself will cost us roughly 20 gigabytes, even if our apps and bin libs together are just 1 megabyte. An equivalent Docker container for that case will theoretically cost us just 1 megabyte. Is that enough to amaze you? And Docker is super lightweight compared to VM because it has improved the shareability between its units. As you can see in this diagram on the left, bins, libs, and guest OS layers are not shared between VMs running MySQL, while on the right, bins lib layer is shared between Docker containers running MySQL. For each VM, there will be a file containing all layers from guest OS up to app. As a result, for two VMs running the same app, there will be two files containing the same layers. For three VMs running the same app, there will be three files containing the same layers. If the guest OS costs 20 gigabytes, then each file will cost at least 20 gigabytes. It means if you have two VMs, it costs 40 gigabytes. If you have three VMs, it costs 60 gigabytes. With Docker, data is structured differently. Instead of using a single file for all layers, Docker uses a file for each layer. So if two Docker containers need the same layer, then they will share the same file. As a result, even if Docker keeps the above 20 gigabyte guest OS, only one 20 gigabyte file is needed and shared between two or more containers. So even if you have 100 or 1,000 Docker containers running the same guest OS layer, you only need 20 gigabytes for them all. But Docker does not save only disk space, it also saves memory and CPU compared to VM. Because VM has guest OS, it will always run a lot of processes needed for that guest OS, but maybe not needed for your app. From your app perspective, it means a waste of runtime resources. Docker tries to eliminate that guest OS and focus on what your app really needs. As a result, it is possible to run just enough dependencies that your app needs. I hope you feel more interested in Docker and want to know more about it now. Let's dig deeper into Docker architecture. As you can see from this diagram, Docker architecture is quite simple. It consists of three parts: client, Docker host, and registry. Client and Docker host parts together are called Docker engine. When you want to use Docker in a machine, you need to install Docker engine into that machine. To send commands to Docker, you use the client part. To receive the commands, you need Docker host. Inside Docker host, there is a Docker daemon. That is a background application that receives commands sent from Docker client. The images box within Docker host represents a local repository of Docker images. A Docker image is merely a set of files corresponding to a bundle of some application. When Docker wants to run an application, it looks for a Docker image, loads the related files into memory, and creates a Docker container. So a Docker image is similar to a template, and a Docker container is a runtime instance of that template. Now back to the client box on the left. It is listing three most popular Docker commands. Docker build allows you to build a Docker image. Docker pull allows you to pull a Docker image from some registry into your local store. Docker run allows you to run a Docker container based on some Docker image. Next, let's move to the registry box on the right. As you can guess now, a registry is a remote store of Docker images. When you create a new Docker image, the image resides on your local machine. You will need to use a Docker command named docker push to push that image to the registry. There are many types of registries. For example, Docker Hub is a free registry. Docker Cloud or Docker Store is a paid registry. If you don't want to use any of them, you can also create your own registry, etc. When you work with Docker, you will often need these terminologies: build, ship, run. In the previous slides, you have learned that Docker is a platform that helps to build, ship, run applications. In the build phase, you write all steps you need in a Dockerfile. For example, you want to bundle a Python application based on the code from some GitHub repository. Then in your Dockerfile, you need to specify all needed steps from getting the code to downloading the needed dependencies to building the app. Finally, you use docker build command with that Dockerfile as input to build the Docker image. In the ship phase, you will need registry, repository, Docker ID. The most popular registry that you will use tends to be Docker Hub. And to push your Docker images into Docker Hub, you need a Docker ID. You can get a Docker ID by registering a free account with Docker Hub. When you have a Docker ID, you can create different public repositories. Each repository contains different versions of the same Docker image. It is possible to use one repository to contain different versions of different Docker images, but it is not recommended. One important note with Docker Hub is, other than one private repository, all other repositories that you create will be public, which means everyone else can see and use it. So, if you don't want to share your Docker images, you may have to consider a paid registry. In the run phase, you will need engine, that is Docker engine, container, a runtime instance of a Docker image, machine. Previously, Docker allows us to create different virtual machines. .yml, the extension of a file that you will need when you work with Docker Compose. Docker Compose is a tool that allows you to easily set up systems based on multiple Docker images. For example, you want to set up a web application system with a React frontend connecting to a Python backend, connecting to a Redis database. You will also want to have 3 instances of React frontend, 2 instances of Python backend, and 1 instance of Redis. Although it is possible to do the same using basic Docker commands, it is much simpler to do so using Docker Compose. Docker has a lot of commands. For beginners, this cheat sheet by Rebel Labs should be enough. It contains the most needed concepts and commands. The next question is, how to get started with Docker? To get started with Docker, we need to do the following things. First, install Docker. Next, register a Docker ID. Then, we get used to basic commands such as run an existing image or build a new image and push it to Docker Hub. After that, we have a look at Docker Hub. And finally, we play a bit with Docker Lab. To install Docker, you can visit docker.com, then select Docker Desktop from the products list. You will be redirected to the Docker Desktop page. Here you can select the proper version matching your operating system. For example, because I am using Windows, I will select Download for Windows. After the download has completed, let it run. Because I use the Windows version, the first screen I see is something like this. It is important that you check Install Required Windows Components for WSL2. WSL is a new feature in Windows 10, which makes it possible to embed a Linux OS inside Windows. There are two versions of WSL, and Docker prefers the second one. With WSL1, Docker Desktop requires Windows 10 Pro version. With WSL2, Docker Desktop can work well in both Windows 10 Home and Pro versions. If you want to find out more about WSL, you can follow the recommended links. During the installation, you can see the progress like this. After the installation has finished, you need to click Close and Restart to restart your machine. If WSL2 is not installed yet, you will see this screen. You can follow the link recommended by Docker Desktop to install the missing parts. In case you still have issues, you can try the links below to resolve them. And after you have finished installing WSL2, you click Restart in that dialog to restart your machine. After installing Docker Desktop, you need to integrate it with WSL2. Right-click on the icon of Docker Desktop and click Settings. This is the Settings page of Docker Desktop. In the General section, there is an important check shown in the red box. Next, go to the Resources section and select WSL Integration. Here you need to check Enable integration with my default WSL distro. Because there's no WSL2 distro in my machine now, there's nothing listed below that check. In order to install a distro, I will visit Microsoft Store. Here I will use a Ubuntu distro, so I type Ubuntu in the search box. A couple of results will be shown, and I choose Ubuntu 20.04. After having installed the Ubuntu distro, I return to the settings page of Docker Desktop and click Refresh. Now Ubuntu 20.04 is shown. I select it and click Apply and Restart. After Windows has restarted, we are done with the Docker installation as well as integration with WSL2. To work with Docker, you will often need a terminal. It is possible to use the built-in Windows PowerShell or command prompt, or you can also install the one named Windows Terminal. Windows Terminal is a modern terminal application that allows you to use different types of terminals via tabs. As you can see, it can automatically detect all types of terminals available in your machine. Each time I need a new terminal, I can just add a tab instead of opening a new separate window. Depending on the Docker Desktop version you use, you may experience a different first screen for the first time you start Docker Desktop. For example, with the version I used, I get a quick 4-step tutorial like this. The first step is clone a repository. The second step is build the image. The third step is run a container. The fourth step is save and share your image. The goal of this tutorial is to show you how simple it is to work with Docker. Only 4 steps. I will use that tutorial to help you get started. And before we start, please notice the link in the red box. If you already have a Docker ID, you can use it to sign in. After that, your Docker desktop will connect to Docker Hub and allow you to pull and push images more easily. If you don't have a Docker ID yet, you can use the link to Docker Hub to register a new one. That Docker ID will also allow you to sign in Docker Lab later. After you have signed in, step 4 will look like this. Now it shows the specific commands you can use to share your image. Click Done to close the tutorial. This is the main UI that you will often use. On the left pane, you see containers, images. Use containers when you want to see all containers in your machine. Use images when you want to see all images in your machine as well as in the connected registry. In later versions, there will be more items such as volumes, dev environments, extensions, etc. Now let's start getting our hands dirty. First, I open two terminals. The first on the left is the built-in command prompt. The second on the right is a terminal from my Ubuntu distro. In the left terminal, I run docker image list to list all Docker images in my local machine. Then docker ps to list all running Docker containers. As you can see, there is no Docker image and there is no running Docker container in my machine. Next, I run the same two commands in the right terminal to make sure that there is nothing there too. Now go back to the left terminal and try a docker run command. The goal is I want to run a Docker image named docker/getting started. In my command, I specify a -d argument. The purpose is to instruct the Docker container to run in detached mode, so that it will not take over this terminal, and so that I can continue typing other commands in this terminal. In my command, I also specify a -p80:80 argument. The purpose is to instruct Docker to map port 80 inside the Docker container to port 80 in the host OS. It means if inside the Docker container there is an application A listening to port 80, then another application B in the host OS can communicate with A via port 80 in the host OS. Let's look at the logs. First, Docker tries to look for the image locally. Because the image does not exist in my machine yet, Docker will pull it from Docker Hub. There are a series of pulls corresponding to a series of files comprising this image. At the final step, a long ID was printed out. That ID is the container ID. Each time Docker creates a new container, it will assign a new unique ID like that. And that ID can be used to remove that container later. Next, I use Docker image list again and find that there is a Docker image now. Similarly, I use docker ps again and also find that there's a running container. Moving to the right terminal and trying the same two commands, I get the same results as in the left terminal. This proves that two terminals are actually two Docker clients connecting to the same Docker daemon running in the host OS. A Docker container can contain a complete environment for a web, console, desktop application to run. And that application can run either forever or just one time. In our case, the docker run command that I used started a web application. To verify that, I can open a browser and visit this link http://localhost:80/. When I press enter, I will see a web page like this. The content of that web page is something you should read if you want to dig deeper into Docker later. If you want to investigate the running containers, you can open Docker Desktop, select Container section, and select the container by name. It will give you something like this screen. You can try clicking on each tab to view different information about the container. There are also a number of buttons which allow you to start, stop, or remove the container. Similarly, if you want to investigate the related Docker image, you can try the Images section. So we have known how to run a Docker image, how to check what images and running containers are available in our machine. What to do next is to try the 4-step tutorial that we saw in the first time we ran Docker Desktop. Step 1 of that tutorial, clone, is to execute a docker run command like this. What it wants is to create a Docker container named repo based on the Docker image name onpy/git. When the container has started, it will execute a git clone command to clone the GitHub repository at the specified URL into the working folder inside that container. Following the logs, we can see that Docker could not find the image locally, so it tried pulling the image from Docker Hub. One of the lines reads, "already exists." Just to remind, a Docker image consists of a set of files. Each file represents a layer in the image, and it can be shared between different images. When Docker pulls an image, it logs a separate line for each layer file. The ID beginning each log line is the ID of the layer in the image. Lines saying "already exists" mean the corresponding layer file already exists in the local machine. No need to re-download. That also means this image and some existing local image share that layer file. The last log line says cloning into something. It is from the git clone command that we specified. Next, I use list command to show you that my Docker folder is empty now. Then I use dockerps command to list running containers. Oh, there's no running container. You may wonder why. The previous docker run command resulted in a running container. Why does this one not? That is because the previous command started a web app that runs forever, while this command started a git clone that runs only once. I use dockerps-a command to list all containers, both running and not running. I see my container now. It exited already. After that, I use dockercp command to copy everything from the folder /git/getting started inside the repo container to the current folder in host OS. Running list again will show that there is something in C Docker folder now. Great. Step 2 of the tutorial, build, requires us to move into getting started folder and execute a docker build command to create a new Docker image named Docker 101 tutorial. The final dot argument means we use the current folder as Docker build context. Docker build context is the set of files that Docker can use during the build process. The bigger the build context is, the slower Docker build initializations will be. When you look at the build logs, you will see lines having the pattern similar to those in green boxes. Such lines correspond to the specified task in the Dockerfile used for the build. Then the question is, What is Dockerfile? As mentioned in the slide listing Docker terminologies, Dockerfile is a file containing a sequence of instructions on what to do to build an application. Docker will use this file to build a Docker image for that application. If you run list command inside docker/getting started folder, you will see that besides Dockerfile, there are also two special files, namely .dockerignore and docker-compose.yml. Dockerignore is a file defining which files and folders will be excluded from Docker context. For example, when we want to exclude all files with .txt extension, we can specify *.txt in dockerignore. Then, during the build, Docker will ignore all .txt files available in Docker context. The other special file is docker-compose.yml. This file specifies how the containers will run together. Docker Compose itself is a huge topic and is beyond the scope of this presentation. As a result, we will not talk more about it. Now let's rerun the last Docker build command and see what will happen. When you rerun the last build command, you will notice that the build is faster this time. Look at the logs. You will see that many lines will be prefixed with cached. That is the outcome of build optimization. We have known that a Docker image consists of a series of layer files. But how can Docker determine a layer? Well, it relies on Dockerfile. Each command in Dockerfile creates a layer. If a command is not changed and its order in the Dockerfile is not changed, then its corresponding layer will not be changed too. When Docker sees that a layer is not changed, it will reuse it. Thanks to that strategy, Docker can build fast and effectively. Now let's use Docker image list command to check what we have created. As you may guess, when we created a Docker image, we actually created a repository having the same name as the image. It also has a tag. Because we did not specify a specific tag in the Docker build command, the image tag was defaulted to latest. Next, in step 3 of the tutorial, run, we start a Docker container named Docker tutorial in detached mode and map is port 80 to port 80 of the host OS. Open your browser and visit http://localhost:80. You will see the familiar web page in the previous slide again. In step 4 of the tutorial, share. We need to push out image to Docker Hub so that others can use. When a Docker image resides in your machine, you can name it the way you want. However, if you want to push a Docker image to Docker Hub, you need to name it properly. The required name format includes two parts, Docker username / image name. Docker does not allow you to rename an image, but it allows adding a new name to an existing image by docker-tat command. Let's use docker-tat command to give a new name to our Docker 101 tutorial image. Then list all the images we have. A new repository has been added for the new name, but image ID is the same. Oh, that is cool. You can utilize docker-tat command to create as many aliases for an image as you wish. Next, use docker login command to log in Docker Hub. Finally, use docker push command to push your image to Docker Hub. When Docker push has finished, your image is ready for use by anyone. To double check, we visit Docker Hub website at https://hub.docker.com and search for our image name. There it is. Docker Hub is a huge public source of Docker repositories. Many popular applications already have the Docker images here. For developers, almost all popular frameworks, programming languages are here too. When working with Docker Hub, you need to remember that a Docker ID is required when you want to push, but not required when you want to pull. So far, we have learned how to create a Docker image, run a Docker container, pull a Docker image to our machine, push a Docker image to Docker Hub, list running and non-running containers. Next, we will look at how to clean them up. For example, there are 3 containers in my local machine. How can I remove them? Well, we will remove containers using docker-rm command. It is possible to remove a container by name or by ID. If we remove by name, then we need to specify the full container name. However, if we remove by ID, we only need to specify the ID head that uniquely identifies the container among the existing containers. For example, if I have 2 containers whose IDs are 102 and 203, if I want to remove 102, then I only need to specify 1, as that is enough to uniquely identify it between 2 containers. After removing containers, we can try removing the related images. First, we list all available images in our machine. Can you see 2 Docker 101 tutorial images? Just to remind, they have the same image ID because they are just 2 names of the same image. When we remove one of them, the log says untag, and the real image is still there. When we remove the other, besides untag logs, there is also a deleted log. Something has been deleted. Yes, all layer files of that image have been deleted. Remember, when we pushed our Docker image to Docker Hub, I used to mention that the image would be ready for use by anyone. It is time to test that. Let's pull it back to this machine. Wow, Docker pull works. The image can be pulled and run as expected, but there are 2 new things with Docker run command here. The first thing is we run a container in interactive mode, not detached mode, using -it argument. When we run a container in interactive mode, the terminal will be taken over by the container. We cannot type more commands. The second new thing is --rm argument, which guarantees that when we stop this running session, the container will be automatically removed. We will not see it even with docker ps-a command. In interactive run mode, logs inside the container will be shown directly in the terminal like this. When you're bored with seeing the logs, you can try pressing the combination key Ctrl and C to terminate the running session. Then you use docker ps and docker ps-a to check whether the container still exists or not. As you can see, the container has been completely removed thanks to --rm argument. So far, I have been using my laptop to demonstrate Docker commands to you. To practice at your site, some of you may use your machines. Some may be more reluctant because they feel that it is risky to experiment Docker in their machines. Some just cannot because they do not have a suitable OS. In the latter cases, is there any solution? Luckily, yes, there is a solution. Docker Lab. Let's open your browser and visit the link in the red box. Then click Get Started in Lab Environment group. You will be redirected to this web page. Select Login Docker and log in using your Docker ID. If you still have no Docker ID yet, then click Sign up to register one. After logging in, click Start to start. In Docker Lab, you can add new instance. Each instance is similar to a virtual machine. Your lab session will last for 4 hours. It means after 4 hours, all instances that you create will be terminated. Here I will click to add a new instance. As you can see, an instance will have an IP address, 4 GB of RAM, some CPU, and an SSH URL. In the terminal of this instance, I will try some Docker commands that we have learned so far. I started with listing all containers. Then I run my public Docker image in interactive mode. Next, I create another new instance. Then from the second instance, I use current command to get data from the web application running inside the first instance. The response proves that the web application is running as expected. The example with Docker Lab is the last one in this introduction to Docker. For your convenience, I have listed all commands that we use so far here. You can test yourself to see how many of them you have understood and remembered. I hope that you have understood and remember all. As a summary, this presentation has focused on 3 questions. First, what is Docker? Docker is a platform for developers and system administrators to develop, ship, and run applications. The second question is, what can Docker do? Based on images and containers, Docker can replicate an environment to run applications consistently. The third question is, how to work with Docker? I have shown you how. What I have shown is not all about Docker, but it should be enough for you to get started. Try it and you'll see. I hope that you find Docker interesting and will get your hands dirty after this presentation. If you have any question, you can put it in the comment section of this video. When I can spare some time, I will try to add my reply. Thank you for listening. Have fun with Docker and see you in another presentation.